Anthony, did you have a question?
Yeah, I think I might have broke something down wrong for the 3 different parabolas.
Yeah, what are the 3 basic scenarios for the relationship between a parabola and the x-axis? Is that the question?
Yeah.
Yeah.
Is one of them where b squared minus 4ac is greater than 0?
Uh-huh. Yep. One is greater, one is less, and one is equal. All right, folks. Let's come back together as a group and discuss these. First, why did mathematicians agree to treat I equals the square root of 1 like an allowable mathematical object? Because the square root of -1 on your calculator is not an allowable mathematical object. It says error. So why did they agree to treat this like a real thing? Brian? Yeah, exactly. They wanted to solve every equation. Every equation, they wanted to have a solution. So even the most basic equation like x squared plus 1, that's a very simple equation. There's just one variable, one term other than it. And they wanted there to be a solution. So in solving this problem, they said, well, it appears that the square root of -1 isn't real. Well, let's just go ahead and call it something. And we'll call it I. And that way we can say that the solution is plus or minus I. And plus, that allows the fundamental theorem of algebra, which is that the highest exponent on x tells you how many solutions there are. So they wanted that if you have an x squared problem, there should be 2 solutions. And now, in fact, there are 2 solutions, plus or minus I. Okay, great. Thank you. And what are the 4 methods for solving a quadratic equation? What were the 4 methods that we did last time? I'll write them up here. Yeah, one of them was factoring. Was that the second one, maybe? They don't have to go in order. But yeah, one of them is factoring. What's another one? Wait, someone just said what? Well, that's true. That's true. If someone said something else beside that? Yeah, the square root property. I think that was the first one. And yeah, square root. And then thank you, Raheem, the quadratic formula. And then there was one other method. Let's see. Now, I don't quite have your names absolutely memorized just yet. But I'm going to try here. Well, I know. Oh, boy. Let's see. Who shall I? What was that? What was the other method? Yeah, completing the square. Okay, very good. All right, so those are our 4 methods. And I think we agreed that the square root property and completing the square were kind of the same, because you complete the square so that you can take the square root of both sides. The quadratic was definitely its own thing, and factoring is kind of its own thing too. All right, so those are the methods that you have. In this class, is there a rule about which one you have to use? Like if you just have to solve a quadratic, can you choose? You can essentially choose, unless the instructions on the quiz or test say use this method. So on the test, if it says use completing the square, you need to use completing the square. But if you wanted to check your work using another method, you could do that. Okay. What does it mean to solve a quadratic equation? What does it mean to solve a quadratic equation? Diego, what do you guys think?
Find out if it's true.
Well, that's certainly true. All equations, we want to find out if it's true. We want to find what number to plug in that would make it true. Yeah, that's absolutely correct. We want to find a number that you can plug in to make it true. And in terms of a quadratic equation, or really any equation, what are those numbers that make the equation true? Yeah, they're x-intercepts. And what did you say they were? Yeah, they're zeros. You can call them zeros, roots, solutions, or x-intercepts. All those mean the same thing. So what are you finding? You're finding a root. You're finding an x-intercept. You're finding a solution. You're finding a zero. All of those words actually mean the exact same thing. They all mean that you're finding the number that you can plug into the equation to make it true, which on a graph happen to be the x-intercepts. Okay, and what does the quadratic formula tell you? The quadratic formula being negative b plus or minus the square root of b squared minus 4ac all over 2a. When you actually calculate that whole thing and you get your number, what is it actually telling you? How about Ryan? What does the quadratic formula tell you?
I don't know.
And that's not fair. You came in a little late. I shouldn't have called on you. I don't know if you had a chance to talk to the neighbor. Nancy? It's either giving you 2 values, or if that's a 0, 1 value, or if that's imaginary, 2 imaginary values. What are those different values? You what? Not sure? Well, that's okay. Someone help her out? What are those 2 values? Yeah? Those are the x-intercepts, absolutely. Yep, that's when you set the equation equals 0 and solve. So this is, in fact, the x-intercepts. In fact, you know how people normally write the formula as x equals, etc.? Well, that really means x-intercept. That's always what you're solving for. It's really x-int. There we go. So whenever you solve the quadratic formula, those are the x-intercepts. All right, and then what are the three basic scenarios for the relationship between the parabola and the x-axis? Anthony, this was your question. What are the three different scenarios?
B squared minus 4ac is greater than 0.
And if b squared minus 4ac is greater than 0,
There are two real solutions.
yeah, that means that that's a positive number, which means you actually are square rooting something. And since you can square root something, that means you're going to add or minus that value, creating two different realities, two different solutions. So definitely that's when b squared minus 4ac is greater than 0. Now what was this one, Anthony?
It's equal to 0.
Yeah. If you plug in a b squared minus 4ac and it equals 0, the square root of 0 is 0, and your plus or minusing is 0, does that create two alternate realities? Like if I have the number 5 plus or minus 0, one reality is 5 plus 0, and the other reality is 5 minus 0, but they're both 5. So there's really just one solution. And that tells me that the parabola just touches down on the x-axis at just one spot. Not two spots, just one spot. So that's if b squared minus 4ac is equal to 0. And what's the other one, Anthony?
When it's less than 0.
Yeah, b squared minus 4ac is less than 0. What does that mean that b squared minus 4ac is less than 0? Yeah, it means it would be imaginary. If b squared minus 4ac is negative, you're square rooting a negative, which means it's imaginary, which means there are no x-intercepts because the parabola is floating up above the axis. So you would definitely want to memorize those. Memorize and understand conceptually what we're doing in the quadratic formula that would lead to these different possibilities. Because you'll definitely have one question on the test where I just give you three different discriminant scenarios and then you distinguish between them. Okay. And then finally, what part of the quadratic formula is the discriminant? And what does it discriminate between? How about Myra? What part of the quadratic formula is the discriminant? Yeah, the b squared minus 4ac. Really just the part under the square root. The part under the square root. Because that's, and what is that distinguishing between? How about Allison? B squared minus 4ac, whether it's negative, 0, or positive, what is it telling you? Yeah, exactly. Whether it's below, on, or above. And those are great words for it. So below, or on, or above. That's what it's telling us. All right, folks. So this is what we did last class. We talked all about quadratics, how to solve them, which in the class 120, if you took 120, that probably would have taken a whole month right there. Just spending a month to talk about different quadratic equations, how to solve them using all four of those methods, what it means graphically, what the discriminant does for you. So we did all that in essentially a day to review from your 120 class. Does anyone have any additional questions you want to ask about that? Okay. Well, thank you very much for bringing up your midway quiz. I'll take these home tonight. Well, I teach until 9:30 tonight, so I won't have a chance to grade these today. But I'll grade them tomorrow, and then hopefully I can get them back to you by Wednesday, so that way you'll have that feedback. So where are we today in the calendar? Let's see here. Today is the 29th. So we're starting section 1.5. I think that's where we actually are. We're starting section 1.5. And on Wednesday, we'll finish off this chapter. And then next week on Monday, February 5th, you'll take your first test. Did I already give you the practice test? I did not? I really thought I did. Let me look. That's that. Oh, gee, I guess I didn't. Well, that's okay. I'll give it to you next time then. The practice test is, it's basically formatted just like the real test. So when I give you the practice test, you're essentially looking at the actual test. It's just that I'm going to change all the numbers and change things a little bit for the actual test. So I'll give you that practice test next time. And on the day of the test, that's when everything is due. So the notes packet that we're taking right now, that's due on the day of the test. The practice test, that would be next time, that's due on the day of the test. And then my math lab homework is also due on the day of the test. Okay. Anyone have any questions about where we are on the calendar? All right. Well then, I have 2 new jokes for you this week. Here's my joke for today. It's a knock-knock joke, so I hope you're all going to reply. Knock-knock. Interrupting cow. Moo. You already heard that joke, maybe? All right, well, I thought it was clever. All right, folks, here we go. Folks, do you know how excited you probably are all right now? Do you know what we're doing mostly today? Word problems. Oh my goodness, this is just the best. I bet you're all thoroughly excited to tackle word problems. Now, what makes a word problem challenging? Okay, yeah, all the words.
Setting it up.
Setting it up. Yeah, that's the challenging part. When you look at a word problem, do they just come out and give you an equation? Like, do you see an equation anywhere in there? No, I see a couple numbers. I see a 4, a 2, and a 169. And, you know, the worst case scenario is every once in a while I see people just take the 4, the 2, and the 9 and maybe multiply them all together and say, here you go, this is the answer. Will that approach almost ever work? You just take a bunch of numbers. No, you have to know what they're actually representing. So word problems are challenging because they haven't told you what equation to solve yet. But will there be an equation to solve? Yeah, absolutely. There will be an equation. Now, I think that we went through this 4-step process last time. I'm not sure if we did or not. So remind me, did I say that the first thing you always do in a word problem is draw a picture? Oh, okay, yeah, so I already started this off. And then what would be the second thing we would do? Do what? Yeah, identify the equation, some sort of equation that you're actually going to use. And then once you actually know what equation you actually have to solve, then you solve it. You know, you solve for x, quote unquote. But then what's always the very last thing you're going to do? Yeah, verify. Trust but verify, right? We want to actually check to make sure that whatever number we came up with actually makes sense within the context of the original word problem. So we verify truth. Okay. So we have a problem here. Everyone just take a moment to read it to yourself once. Go ahead and read it to yourself. All right, so let's read this out loud. Now, when you read a word problem, I have some recommendations for you. First, you can read it all the way through if you like, just to know what the problem is about. So the length of a rectangle is 4 inches more than the width. If 2 inches are taken from the length and added to the width, the figure becomes a square with an area of 169 square inches. What are the dimensions of the original figure? So in just 2 words, or even 1 word, what are we talking about? Okay, that's true. We're talking about area. We're talking about length times width. But what object are we talking about? We're talking about a rectangle, right? We're talking about a rectangle. Now, you could also say we're talking about a square. And that's true. We seem to be talking about both. We're talking about a rectangle. We're also talking about a square. But what's the question asking? Yeah, and what's the original figure? A rectangle. So fundamentally, in this problem, we're talking about a rectangle. If somebody asks you that, what's this problem about? You'd say, well, it's about a rectangle. And then what do you do to that rectangle? Fundamentally, you're taking away some of the length, adding it to the width, but what do you do to the rectangle? You turn it into a square. And then they give us some information about that, and then from there we have to solve the problem. So fundamentally, if you just wanted to wrap your mind around the problem, you'd say, okay, this problem is about a rectangle that gets turned into a square, and they want to know what are the dimensions. So what are the dimensions? So when all is said and done, the form of your answer should be the dimensions of the original figure, which would have, you know, say a base, a height, or a length times a width. That's what we're looking for. Okay, so going back to the beginning then, you read the problem again and go very slowly, drawing a picture as you go. So the length of a rectangle. Stop. Let's go ahead and draw a rectangle. This is us beginning the problem. We're going to draw a rectangle. And definitely make it rectangular-ish, not square-ish, because in a moment we're going to draw a square. And you would hope that your audience would be able to distinguish between which one of your drawings is a rectangle and which one is a square. Every once in a while I see people go like this. They're like, here's my rectangle, here's my square. And I'm like, what's the difference between them? Because honestly, they both kind of look the same, just sloppy line figures. So we really want to exaggerate and make sure that one is a rectangle and one is a square. Okay, so the length of a rectangle is 4 more than the width. how do we capture that information? It's 4 more than the width. David, what do you think? How do we capture that information? That the length is 4, well, whichever one of these we're calling the length, but this one is 4 more, and this one looks longer, so it's 4 more than that one. How do I write that down? Yeah, this one would be the x plus 4, because it's 4 more than. And then what's the other one? The what?
Or X.
Yeah, just x. This is a really good setup, folks. Almost always in math, you choose the smallest thing to be x. And since this thing is 4 more than that one, the smallest thing would be the x alone. And then this one's 4 more than that, so that's the bigger one. Okay, so that's our setup. The length of a rectangle is 4 more than the width. If 2 are taken from the length and added to the width, the figure becomes a square. So I'm going to draw a little line, a little arrow that is, and now I'm going to draw a square-looking square. How did I do? Would you believe that that one's the square and this one's the rectangle? Like, again, you want to be mindful of your audience. Really make it look like a square if you can. So now how do I capture this information? 2 are taken from the length and added to the width. What should we do? Michael, what do you think?
Make both sides X plus 2.
Yeah, you would make both sides x plus 2. And why is that? Because here, I'm going to subtract 2 from the length. And then here, I'm going to add 2. So if you do those 2 operations, you're subtracting 2 from here and adding 2 to here, here you would be left with x plus 2. And then here you'd be left with x plus 2. Yeah, really nice. Now they're saying the figure becomes a square with an area of 169 square inches. So the area, what's the formula for area? Yeah, length times width. So now we finally have a formula. Area equals length times width. And what will we plug into that formula? We know we have the length and the width. We've got that x plus 2 times x plus 2. And what is the area? Yeah, 169. So we have a pretty nice formula here, folks. Now, we're totally done with number 1. We drew some really nice pictures. We're done with number 2. We have our equation. This is the equation we want to solve. And now the question is, which of our 4 approaches to solving a quadratic do we want to use? Do we want to do the square root property, factoring, completing the square, or quadratic? Someone said factoring? You could factor. And as a matter of fact, you could do any of these. Any of these are open to you. Now, before anyone writes anything down, let's just look a second at factoring. So x plus 2 times x plus 2 equals 169. Can I go ahead and do the whole factoring thing right now and say, well, hey, x plus 2 equals 0, x plus 2 equals 0? Can I set both of those equal 0? Why not? Yeah, because it's not equal to 0. I can't say this times this equals 0 because, in fact, it's not equal to 0. It's equal to 169. So without doing it, just watch. If I really wanted to factor this problem, I would first have to FOIL it out to get x squared plus 2x plus 2x plus 4. I would have to combine all my like terms, so x squared plus 4x. I'd have to subtract the 169 over to the left, and then I would have x squared plus 4x minus 165 equals 0. Now I have an equation that's equal to 0. And only now could I either factor, which is what multiplies to make 165 that adds to make 4, or I could do the quadratic formula, right? A is 1, B is 4, C is negative 165. Or I could complete the square by moving that negative 165 over to the right. Yeah, and it really doesn't look like I can do the square root property at this point because I don't have one thing squared. So out of all those different methods, which one do you want to do? Maybe factoring, because right now we could just say what multiplies to make 165. And in fact, I think 165 is 15 times 11. Pretty sure.
Yes, because 15 minus 11 is 4.
Yeah, exactly. So this would be x plus 15 times x minus 11. And so this would be the factoring approach. And so x plus 15 equals 0, or x minus 11 equals 0. And so we have x equals negative 15. Can that be the answer? Negative 15? No, it's negative. That doesn't make sense. Or x equals 11. Would that be the answer? Yeah. So that means in my original problem, x is 11, and therefore 11 plus 4 is 15. Right? This answer would be 15, and just 11 would be 11. And theoretically, then that would be our answer. Now, folks, I realized I told you not to write any of that down, because I was just kind of showing you different options. let's go back to the actual original problem. What would be our best method for solving this with the least amount of work? What do you think, Regan?
Put x plus 2 squared.
Yeah, you write x plus 2 squared. You say x plus 2 squared, and why do you write that as squared? Because then you can just square root both sides, right? That's much easier than everything I just did over there. So you square root both sides, and what does that tell us? X plus 2 is equal to, well, I'm going to move my equal sign and put the 169 over here. Plus or minus 13. Oh, that was just a typo. There we go. Thank you. So we have x plus 2 equals plus or minus 13. And then we'll go ahead and subtract the 2 over. And that gives us x equals negative 2 plus or minus 13. And remember, that's two different realities. That's two different scenarios. It's either the plus 13 or the minus 13. And that gives us what? Negative 2 plus 13 or negative 2 minus 13, which you'll notice gives us the 11 and the negative 15. Are those the same answers that we got by doing factoring? Yeah, but remember, this way took a lot more work. We FOILed it out and then tried to factor. It took a lot more work to do it this way. So we wouldn't want to do it the long way if we don't have to, when we could just do it like this. So number 11, I'm going to go ahead and write that's the answer. And we already said that negative 15 doesn't work. Why doesn't it work? Yeah, because a rectangle can't have a negative width. So folks, there's a word for this. When the algebra gives you an answer that doesn't work in the context of the original problem, everyone write this down, it's called extraneous. Extraneous. It's an extraneous solution. It's extraneous because, in fact, if I plug negative 15 into this equation, it will, in fact, make it true. If I plug negative 15 into that equation, and I'll just show it right here real quick. If I do 169 equals negative 15 plus 2 times negative 15 plus 2, guess what happens? It's negative 13 times negative 13. And what's negative 13 times negative 13? Positive 169. So is negative 15 a solution? No. It makes the equation true. But is it realistic? No. And that's what extraneous means. It means it makes it true, but it's nonsense. Because to the circumstance of a word problem, you can't have a side like this negative 15. All right. So we solved our problem the fastest way possible, which was using the square root property. We now have what we know x to be, which is 11. So how do we report our final answer? Like, what would you put over on the answer line up there? More than that, it says, what are the dimensions of the original figure? So if you wanted to be nice to your audience, would you say the dimensions are, remember the original figure was x plus 4 and x. So that means 11 plus 4, which is 15, and just 11. So you have a couple options. You could either say the answer is 11 by 15 inches, right? That's the full answer. It asks for the dimensions. Or you could just draw a picture. And if you just drew a picture of a rectangle that had an 11 and a 15 on it, that would be very audience-friendly, wouldn't it? That'd be very audience-friendly. Because then your audience would look at it and say, oh, aha, that is the original figure. That's the rectangle. All right. Well, folks, that's it. That problem is done. Now, again, could you have solved that with any other method? Sure. You could have done it in any of the other 4 ways that we talked about. But that way was definitely the fastest. So let's go ahead and try the next one. Go ahead and read it on your own again. Just kind of read it and see what the problem is about. Don't even try to solve it yet. Just see what the problem is about. Imagine it in your mind. Okay, so someone walked in off the street and they said, what is number 33 about? In a very short sentence, much like a cave person, What would you say this problem is about? Someone said, hey, what is this problem about? Nancy, what would you say? Exactly. It's about a rug being fit in a room. That's what you would say. Okay, we've got a room and a rug in it. So we could go ahead and start to draw that. Here's our room. And what do we know about the room? Well, okay, so at this point we should just start reading the problem again very slowly. A rug is to fit in a room, so that a border of even width is left on all four sides. What does that mean? Is the rug gonna fill the room completely wall to wall? No, you're gonna have a little gap at the end, right? So that all those dust bunnies can collect, and then you have to sweep them up. So what does that mean then? The rug should look something like this. That way, this is the actual rug. This is the actual room. And then this distance right here, that's a border going around the room. Right, just a border. So you can actually see the hardwood floor, or you can see the tile, or whatever. So what do they tell us? We know that the room itself is 12 by 15. So I'm just going to go ahead and put 15 and 12 right here. Did I make my picture look like a rectangle or a square? Kind of looks squarish, doesn't it? That's not the best for your audience, because then your audience might think that it's a square, and then they might do math as if it's a square. It's not, in fact, a square. It should have been a rectangle. And you know what? I can fix that real quick. Just going to make it a little longer. Wow, now doesn't that look amazingly better? It looks amazingly better. It's obviously a rectangle now. All right, so I've got my 15 by 12. And what else did they tell us besides the 12 by 15 feet? Robert, what else did they tell us?
108.
Yeah, the area in here is 108 square feet. 108. There we go. There's the tricky thing. What's the actual question? What's the actual question, Roy? What are they actually asking?
How wide would the border be?
Yeah, how wide will the border be? Well, folks, how wide is the border? Yeah, X, we don't know. We have no idea. So we know that that distance right there is X, and this distance over here is X. And we know that this distance up top is X. We know that this distance down at the bottom is X. Because they said that the border was even width. Now, folks, if you've got this drawing on your paper now, have we captured all the information from the word problem? Have we captured all of it? It's a rug fit in a room, so there's border of even width. The room is 12 by 15. The area is 108. How wide will the border be? That's X. Did we get it all? Yes. Yes, we did. That's all the information from the problem. So now that we've drawn a really nice picture, what's our equation? What did you start to say? One thing that we could calculate is the whole area of the whole room, right? Couldn't we do that? The whole room, and I'll just go and write that down. The whole room. I don't know if we need this information or not, but the whole room is area equals length times width, which is 12 by 15, which is what? Is that 180? Yeah, it's 180. All right, well, that's nice to know. You know, we're trying to solve for the width. What else could we write there? Now that was the whole room, right? The whole room. What did they actually tell us the area of? Just the rug. Do we know the dimensions of just the rug? Is the rug 15 feet wide? No, how wide is the rug actually? It's bigger or smaller than 15? Smaller, how much smaller? If you were just to look at the width of the rug, it's 15 what? Minus this X, because you're taking off the width over there. And also minus this X, right? Because you're taking off the width over there. So what's the width of just the rug? Is it 15 minus X minus X? Would that be correct? So it's 15 minus 2X. We can just combine like terms. Yeah, the width of the rug is 15 minus 2X. So we're going to jot that down, that the width of the rug is 15 minus 2X, and make sure you believe it. That if you're just looking at the width of the rug, you have to shave off those borders on the right and left-hand side so that the width of the rug is just 15 minus 2X.
Why do you have 2X?
Well, because you're shaving off, here, look, this little bit of X right here, that's really right here, right? There's the X, and then over here, dropping down from right there, that's another piece of X. And we're just wondering how wide from here to here, right? Just the width of the rug. So it would be the full thing of 15, but you're subtracting off that little x, and you're subtracting off that little x, and that leaves you with 15 minus 1x, and then you combine like terms, and that gives you 15 minus 2x. Does that answer your question? Okay. Folks, believe it or not, we're going to see this word problem or problems like this rather frequently. So understanding the concept of how this works is very important. Raheem, the full width is what? 15. Yeah. But if you shave off the border on the left and you shave off the border on the right and you're just looking at the width of the rug, it'd be 15 minus 2x. So likewise, folks, how tall is the rug? Well, the whole room is 12 feet tall. What about just the rug? That would also be 12 minus 2x because you're shaving off this width, the height of x at the top, you're taking off the height of x at the bottom, and you're just looking at the height of the rug itself, which would also be 12 minus 2x. Now my diagram is now very, very full. I'm going to make a new picture of just the rug so that I can see it. Here's just my rug. And my width is 15 minus 2x, and my height is 12 minus 2x. And what do I know about the rug? What did they actually tell me about it? The area is 108. So now we're getting really close to being able to set up our equation. So what equation could we set up for this rug that has a width of 15 minus 2x, a height of 12 minus 2x, and an area of 108? What would be our equation?
12 minus 2x times 15 minus 2x.
Equals? Yeah, and folks, I would write it down as the formula first. Area is length times width for the rug. The area is 108. And the length is 15 minus 2x. And then the height is 12 minus 2x. And that is our equation. That's the actual equation that we are now going to solve. How much time and energy did it take for us just to get to that point? A fair amount, right? That's to be expected. It's to be expected that it's going to take a little time and energy just to figure out what the problem is about, a rug in a room, to write down all the information on a really good diagram so you can see what's happening, and then you come up with the equation on your own because no one's going to give you the equation. You have to come up with it on your own. All right. Now, did we even need that whole area of the whole room is 108? I'm sorry, 180? We didn't even need to know the area of the whole room is 180. That was something that we didn't end up using. It's not a problem that we calculated it. That's fine. But we just don't need it. So now what are we going to do? What are we going to do with that whole expression? We want to solve it. Are we going to solve it using the square root property, factoring, completing the square, or the quadratic? Can we do the whole square root property like the previous problem? No, because it's not the same binomial. They're different binomials, so we can't just say, 15 minus 2x squared and then square root both sides. So we can't do the square root property. We could factor it, but we'd have to first FOIL it all together and move all the terms to the left. Completing the square, I doubt anybody wants to do completing the square, not even me. And then the quadratic formula, well, we could do the quadratic formula, but again, we have to FOIL all that information together and then push all the terms to the left. So folks, let's go ahead and do that. Almost always, what you're going to need to do is take your two binomials, FOIL them, and move all the terms to the left. So let's go ahead and do that. You'll notice I went ahead and I rewrote it so that all the variables were on the left, because ultimately, where are all my terms going to be? All the terms are going to be on the left, right? That's standard form. You want to put all the terms over on the left. So go ahead and start FOILing. You've got your first, outer, inner, last. So first is 180. Outer is minus 30x. Inner, minus 24x. And last, plus 4x squared. And all that equals 108. Now again, remember, we are now distinctly on phase 2, right? We're totally done with phase 1, drawing the picture and coming up with the equation ourselves. Oh, that was phase 1, draw the picture. Phase 2, we came up with the equation. Phase 3, now we're actually doing algebra. So what do I have to do with this now? Brian, what do I do next? I combine like terms, and I'm even going to rearrange the terms because my x squared term should go first. So I'll say 4x squared, and then minus 54x, and then plus the 180, equals 108. What do I do next? Julian?
And you move the 180.
Yeah, well, not the 180 to the right. Yeah, the 108 to the left, because we always want everything on the left. And why do we want everything on the left? What's so important about everything on the left? What's so important about everything being on the left? Why is this called standard form? This is called standard form for a quadratic equation. What's so standard about it? What's so important about it? That it's equal to 0. Exactly right. I made that blood red there to make a very important point. You need everything equal to 0 because how else would you factor? Right? Factoring, you have to set it equal to 0 so that you can say that binomial times that binomial equals 0, and then you can solve each binomial. The quadratic formula. In order to even do the quadratic formula, it has to be ax squared plus bx plus c equals 0. So that's a standard approach, folks. Anytime you're going to solve, it has to be equal to 0. Okay, so now what does everyone want to do? You want to just do the quadratic formula with a equals 4, b equals negative 54, and c equals 72? You can. Oh, you don't want to do that, Nancy? What would you rather do?
Maybe factor. Find, when I see it, yeah, right there.
You could try to find out what multiplies to make 72 that adds to make 54, but we can't do that yet because there's a 4 in front. What could we do to simplify this whole problem? Divide everything by 4, right? Let's go and do that. Let's divide everything by 4. Does 4 go into 54?
13.5,
Oh, it doesn't go in.
only 2. You have to divide everything by 2.
Wait, really? 54? Oh, yeah. Yeah, we can only divide by 2. 4 doesn't go into 54. And one thing for sure we don't want to do is end up with decimals. So now we have 2x squared minus 27x plus 36 equals 0. All right. Now, at this point, you really do just have to choose what you want to do. Are you going to do the square root property? No, that's not available to us. Are you going to factor it? You can if you want to. Are you going to complete the square? You can if you want to. Are you going to do the quadratic formula? You can if you want to. So everyone in the room could do a different solution at this point, and you can feel free. Why not? Everyone in the room, go ahead and choose whichever way you want to do it. And let's all take 2 minutes to solve the problem in the way you prefer. You can talk it over with your buddy, you can work with your table buddy, or you can just do it on your own. But we should all be solving 2x squared. Nice diagrams, folks. Your pictures of that rug in the room is really good. I didn't put it up. Just in case you want to use the quadratic formula, which is probably how I'll do it, it is negative b plus or minus the square root of b squared minus 4ac all over 2a.
Does 180 go here or 36?
36. So go to the C there. Yeah, I like how you start with C. So you have that negative b. A b itself is already negative. Oh yeah, you have negative. Yeah, we don't do that. It's just using numbers. So you can go
So none of these.
yeah, none of those x's. Yeah. Yeah, really good.
So we're
Get rid of that, because we're only looking at the coefficients, just the numbers, 2, -27, 36. Yep, so then you have b, so minus, oh, I'm sorry, you do need the square, because that's b squared, I'm so sorry. That's not, yeah, I put parentheses around it. Sorry. But the square would go out, because you're squaring negative 27. Yeah, there we go. Negative 27 squared, and then minus, the formula is minus 4ac. Yeah, there you go.
So folks, I think maybe we should check both ways. Should we? Let's see both solutions just for those of you who did it one way or the other. So if you did 2x squared, what was it, minus 27x plus 54? No, that's not right. 36. Is that it? Okay. Who did the quadratic formula? Okay, but probably about half of you. Great. So if you did the quadratic formula, your a is 2, b is -27, and c is 36. So you would do negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. Now all of that you could plug into your calculator, right? I wouldn't plug it all into your calculator all at once. That could be catastrophic. I would just calculate little bits at a time. So for instance, I'm just going to calculate, for instance, a negative right there is positive. So now I have 27 plus or minus the square root. I'm just going to do the 27 squared, which is 729. And then I'm just going to do 4 times 2 times 36, which is 288. And then on the bottom, I'm just going to do 2 times 2 is 4. Like baby steps. Make sure your calculator doesn't give you an error. So then 729 minus 288, that gives 27 plus or minus the square root of 441 all over 4. And that was handy because the square root of 441, what is it? They're 21. It actually square roots. So now we have 27 plus or minus 21 all over 4. And again, that's my 2 different realities. At that point, I draw my arrows. I say, well, in one reality, that's 27 plus 21 over 4. And another reality, that's 27 minus 21 over 4. And then that's what? 48 divided by 4 is 12, or 6 over 4, which is really 1.5. Now, what did we just solve for? What does that number represent in the original problem? Where is my original problem? Oh, yeah. It represents what? X, right? And what was X? It's the what of the room? The border, right? It's the border. So what sounds reasonable to you? Could the border be 12 feet wide or 1.5 feet wide? Could the border be 1.5 feet wide or 12 feet wide? Now, 1.5 is the only reasonable answer. After all, what would happen if the border were 12 feet wide? I mean, how wide is the room? 12 feet. So you can't have a room that's 12 feet tall and then the border be 12 feet because then there would be no rug. So what do we call the answer 12? Extraneous. It makes the equation true. Sure enough, if I plug 12 into that equation, it will be true. But it makes no sense in the context of the problem. So 12 is extraneous, whereas the 1.5 seems good. It seems like the border of the room is 1.5 feet. Now, do I really know that yet? Have I plugged 1.5 into this to check to see if it works? We should probably do that. So what was the dimension of just the rug again? The rug was 15 minus 2x and 12 minus 2x. Well, if x is 1.5, what's 2 times 1.5? 3, and then 15 minus 3 is 12, so apparently the width is 12. And then 12 minus 2x, if x is 1.5, 2 times 1.5 is 3, 12 minus 3 is 9, and apparently the dimension of the rug is 9 by 12. Is that correct?
9 times 12.
9 times 12 is 108. Okay, so there, the problem is just finished. We just finished the problem right there by verifying that the dimension of the room, 9 by 12, really does equal 108, which was the information they gave us in the problem. All right, so that was the solution using the quadratic formula. You got 2 answers, but one of them was extraneous, and now we know the actual answer. The question was, how wide will the border be? That's the answer. You'd come over here to your final answer, and you'd say, border equals 1.5 feet. Right, that's the final answer, is you're answering the question they asked, right? from the solution that we did from the quadratic formula. The quadratic formula gave us 12 and 1.5.
At 1.5, isn't that 3/2?
Yeah.
If you put it in a calculator, that's 1.5.
Yeah, both are correct. If you want to say the answer, 3/2, you can do that. However, I recommend you think about your audience. If you went into Home Depot and you said to the person at the wood cutting station, I'd like a piece of wood that's 3/2 feet long. What do you think that Home Depot employee will say to you?
Yeah.
3/2 feet long, what? Say 1.5, right? You would tell someone at Home Depot 1.5 feet. You would never say 3/2. Imagine if you ordered a pizza. You're like, hi, I'd like to order 3/2 of a pizza. Again, they would ask you what you're talking about because that's not how you speak to an audience. You would do it in the 1.5. So you're right, bringing the answer is 3/2, but we'd say 1.5.
I plug in the 12 and got -12 and -9. So it's positive.
Correct. Yeah, folks, if you do plug in 12, the other answer, you will actually get -12 and -9 for the dimensions of the room. And -12 times -9 is still 108 feet. So it still makes the problem true. But can you have a room that's -12 feet wide and -9 feet tall? You cannot. Yeah. So this is really exciting, folks. First of all, are these long problems? Yeah, I would think all of you would nod your head in agreement. These are long problems. But they're such good, satisfying problems because there's so many places you go. You've got the drawing, you have to figure out the equation. You have to set the equation up in order to solve it. Then you actually have to do the quadratic formula or factoring. Then you have to check if your answers work out in the context of the original problem and get rid of an extraneous solution. This is a long problem, but it's a very good problem. Myra? Why did I? Well, because if you had divided by 4, you would have gotten x squared minus 13.5x plus 18. And I just didn't want a decimal right there. Now, Myra, is there anything wrong with a decimal? No. You could have plugged that decimal into the quadratic formula, and that would have been fine. So, Myra, by all means, if you wanted to divide it all the way and get that decimal right there, you can. But then you're limiting yourself to just doing the quadratic formula. Factoring wouldn't have been as easy then. Yep, you did so Myra, you did the quadratic formula on this? Oh, on the original. Oh, great, Myra did the quadratic formula on the original and she got the same answers. But of course, we would expect that. This equation and this equation and this equation all have the same answers. Okay, folks. Now I realize we just spent quite a bit of time on 2 problems, but I really want to model for you how a problem like this goes and what your work should look like. You should have distinctly phase 1 of a picture, phase 2 of an equation that you identified, phase 3 where you actually just solve for x, and then phase 4 where you actually convince yourself that one of the answers could be extraneous, maybe they're both fine, you don't know, but you have to go back and figure out, did it really make sense in the context of the problem? So yes, these are long problems. Okay, let's try another one. Wait, where's my board? Everyone take a moment to read the question and figure out what the problem is about. Generally speaking, if someone walked up to you and said, hey, what's number 34 about? You would say, all right, let's see here. Jake, what's number 34 about? Very good. It's about 2 cars, folks. And what are they doing, Jake? Or what did they just do? Right? So if somebody said, what's this problem about? You'd say it's about 2 cars that just left an intersection. I think you can all imagine that in your mind. Because you probably all drive or you've been in a car. So you just imagine 2 cars leaving an intersection. Let's read it carefully. 1 car travels north. So I'm going to go ahead and put a dot. This dot represents the intersection where they just left. 1 car went north. So there, I just put a little arrow showing that that car went north. The other went east. So never eat soggy waffles, however you memorize that. East, the other car is going this way. Do we need to draw west and south? No, we don't need west and south. So when the car traveling north had gone 12 miles, all right, so I'm gonna put a little dot here. That's where my car made it to. That distance was 12 miles. So by the time the car going north had gone 12 miles, the distance between the cars. Well, what's the distance between the cars? Where's the other car? Right, we have no idea. But is the other car here, or is the other car still at the intersection? They're over here somewhere, right? So I'm going to go ahead and put a dot. There's my other car. We assume they left the intersection, right? So that other car is somewhere over there. And it says the distance between the cars. How do I represent that? What does that look like? It's the what, Jake? Well, maybe it's X. We're not sure quite yet. But on the drawing, how do I draw the distance between them? You draw a line, which in this case is the hypotenuse, right? We're going to draw a hypotenuse. Now I call it a hypotenuse. The hypotenuse is the diagonal side of a right triangle. Folks, is it fair to assume that this is a right triangle? Everyone put a little right angle mark. Is it fair to assume that most intersections are right angles? Yeah, especially in Arizona. In Arizona, most of our intersections are right angles, unless you have the extreme bad luck to be on Grand Avenue, right? Then you've got this crazy diagonal street cutting across town. Or maybe if you live in Boston or somewhere on the East Coast, intersections would not be right angles. But in this problem, we just have to assume that it is a right angle. Okay, so now the distance between the cars is 4 more than the distance traveled by the car heading east. So which should be X? The distance between them or the distance the car went going eastbound? Which one should be X? It says here the distance between the cars is 4 more than the distance traveled by the car going east.
1 plus X.
So what?
1 plus X.
Yeah, the hypotenuse would be X plus 4, and this distance would be X. Now, but folks, do you all agree? Do you agree? Because the problem says the distance between the cars is 4 more than the distance traveled by the car heading east, and we don't know how far the car heading east has gone. Okay. We've read the whole thing. How far had the eastbound car traveled? So what are we trying to solve for? We're trying to solve for X, right? The eastbound car. Are we done with phase 1?
Yes.
Yeah. Did our picture capture all the information? Have we captured all the information? Car going north went 12 miles. This guy going east, we don't know how far he went, but we know the distance between them is 4 more than him. So yeah, we've got it all. We did make the assumption that it's a right triangle. For all we know, it's not a right triangle. But the assumption that it's a right triangle is key. Because what formula are we going to use? Yeah, a squared plus b squared equals c squared. Now, how on earth are you supposed to know that it's a squared plus b squared equals c squared? Like, you know, before, what's your name again? Gabby? Yeah, before Gabby just said a squared plus b squared equals c squared, why would you have known to use that? I mean, maybe just because you're looking at a right triangle, you're like, well, it's a right triangle, so maybe I'll use the Pythagorean theorem because that relates the side lengths. Of course, I told us to put the right triangle mark. You know, if we didn't know it was a right triangle, we'd be out on a limb. We wouldn't even know what to do. But we made the assumption it's a right triangle, so we can make the assumption that we use. What is this theorem called again? Pythagorean. So everyone, go ahead and write it down. Pythagorean theorem. If I could go back 2,000 years to the meeting where they were like, okay, let's call this thing Pythagorean theorem, I would have stood up in the meeting and been like, no, call it Bob. Bob's theorem. That's fine. But no, we call it Pythagorean. All right, so what do we plug into all this? What does the A and the B represent? What does the A and the B represent? Right?
A is opposite.
Well, in trigonometry, you do have specific sides like sine, cosine, tangent. In the Pythagorean theorem, the A and the B are the legs. It doesn't matter which is which. The A and the B are the legs. And in fact, for that reason, I call the Pythagorean theorem leg squared plus leg squared equals what? Not the distance, the specific word, the hypotenuse. Yeah. This would be a really good way for you to memorize the Pythagorean theorem. It's leg squared plus leg squared equals hypotenuse squared. It doesn't matter which leg you put in when. You just have to put in the two legs. So what's our formula going to be?
12 squared x squared plus x.
Well, what are my two legs? Yeah, 12. And my other leg is x. I'm going to choose to put x first and then 12. And then my hypotenuse was x plus 1. Does everyone agree? Can we set that up right? Okay. Well, we're done with phase 1. We drew a nice picture. We're done with phase 2. We finally have an equation. So now we'll actually go ahead and solve the equation. So what should we do? Remember, ultimately, we want to turn every quadratic into standard form, where you've got ax squared plus bx plus c, all the terms on the left equals 0. So what do we have to do to this equation? Especially this part, what do we have to do? We have to FOIL. We have to FOIL everything. X squared is just x squared, and 12 squared is just 144. But now over here, x plus 4 squared, if you want to do a little scratch work somewhere else. So write it out, x plus 4 times x plus 4. Because x plus 4 squared, you have to FOIL that. You just can't square the x and square the 4. You have to actually FOIL it out. So with FOIL, I have first x squared plus outer 4x plus inner 4x, and plus last 16. And then combining your like terms, x squared plus 16x, I'm sorry, 8x plus 16. Now, folks, sometimes I recommend that. Sometimes I recommend to keep your work nice and clean, go somewhere else and do your scratch work. You know, you don't have to do the scratch work right where you're doing the problem, because this we're trying to keep nice and clean so that you can see the progression of your work. Now what do we do? Ooh, this is exciting. Something really exciting is about to happen, something that all of you will really appreciate. What's about to happen as we solve this problem? Yeah, the x squareds cancel out, right? We're going to move everything to the left, and if you move the x squared to the left, they both cancel out, and this is no longer even a quadratic equation. Right? Now we just have 144 equals 8x plus 16. This is just a very basic equation in a single variable of x. This is wonderful. Do we have to square root property factor, complete the square quadratic formula? We don't have to do any of that. We just go ahead and solve. So I'll go ahead and minus the 16 over, which is what? What is it, 128? So 8x equals 128. Sorry, I ran out of room. 8x equals 128. And then divide off to 8, and what do we get?
16.
Well, goody. 16 what? Miles of who? The eastbound car. Because we just solved for x, and x is on the bottom of the triangle. So the eastbound car, let's go ahead and draw our answer. This person drove 12 miles, this person drove 16. And what's the distance between them? 20. 16 plus 4 is 20. This would be your answer, right? Well, technically the answer, they're just asking for the eastbound car. But if you really wanted to be quite, professional about it, you could write a triangle, which is 12, 16, 20, and circle the 16 and say 16 miles. That would look like a really good answer because you're showing the full context. Now, by the way, are we right? There are two ways we can find out if we're right. You can look at the answers in the back, right? And are we right?
Yes.
Yeah, we are. It's 16. What's the other way, the mathematical way? How do you always confirm your answer? You plug it back into the original formula. And in our case, the original formula is the Pythagorean theorem. So let's try it. Is 12 squared plus 16 squared equal to 20 squared? You'd have to plug all those into your calculator and find out. Do those numbers really make a right triangle? 12 squared is 144, 16 squared is 256, 20 squared is 400, and 144 plus 256 is 400. And right then you give yourself a huge smiley face, because this is where the problem ended. That right there was the end of the problem. Because remember, when does every algebra problem end? in a statement that is true, a true statement. That's the end of an algebra problem. Because right there, we're like, oh, good. The number we found, x equals 16, when I plugged it into the original problem, actually made a true statement. And that's the end of the problem. Okay. Wonderful, folks. Boy, talk about some exciting problems. Folks, it is break time. But just to move us along a second here, let's just look at 35. What is the problem about? You could probably just read the first sentence. A ladder leaning against the wall, right? Everyone, let's go ahead and draw that. Maybe you want to draw a building. Here's the ground. And then you draw a ladder leaning up against it. How did I do? Is it the most beautiful picture of a ladder leaning against a wall you've ever seen?
Breathtaking.
Breathtaking, thank you. I think it looks very good. So the ladder's resting against the wall. The top of the ladder touches the wall at a height of 12. So that height of the wall is 12 right there. That distance from here to here, that's 12. And it says here, find the length of the ladder if the length of the ladder is 4 more than the distance from the wall. So we've got a ladder length and the distance from the wall length. What do I label them? Yeah, the length of the ladder is 4 more than the distance of the ladder from the base of the wall. We don't know how far that is, so we call it x. Okay, so silly enough, folks, this is actually the exact same problem, isn't it? It's identical, isn't it? Instead of cars at an intersection, it's a ladder leaning against the wall, but it's literally even the same numbers.
Would the answer be the same?
The answer will be the same as well. So the length of the ladder, we all know, is already 20, and the distance from the wall is 16, because it's technically the same problem. So do you have to solve number 35? No. But do draw a picture. Everybody, you have to draw a picture only, and that's it. You don't have to do the whole problem again, because obviously it's the same numbers. It does? Now, it says find the length of the ladder. So what should the answer be? 20. Is that the answer? Yeah, there you go. See, they were asking for different things. In the previous problem, they wanted the distance of the eastbound car, which was the leg on the bottom. In this problem, they're asking for the length of the ladder, which is the 20. So that's very subtle, and that's why the answer in the back is different. All right, folks, the time is 9:07, so everyone will be back in the room at 9:16. Is that the quiz?
Yeah.
Oh, you rewrote it anyway.
Yeah.
All right, I appreciate that. Here, I'll take it
Because I
from you.
didn't really stop me.
I appreciate that. I was trying to save you the extra work, but hey, I appreciate that you take pride in your work. Here you go. Thank you. Hey there, Brad. How can I help you?
Do you know if maybe sell like chargers for these? 'Cause
I don't know about chargers. I think, does it not take batteries?
No.
Oh,
It's like the
geez.
older.
Oh, yeah. No, I have no idea. Yeah, where have you had this a while?
Yeah, I had it a while. I just.
Yeah, the battery's dead. Yeah, sorry. I don't know where you can get a charger for that. You might just have to Google Amazon and see if it has it.
I just use the same charger. It's just that one has a charger on it.
Yeah.
So they had it like a charger.
Yeah, sorry, I don't have it. Hi there. I was calling back Ruben. Is he around? Yes, my name is J.W. Gabriel. You sent me a phone call. Okay. Hey, Ruben, this is J.W. Gabriel. Thank you for the voice or the text. So yeah, you need my email address? It is euclida@hotmail.com. So I'll spell it out for you. EUCLID as in dog, UB as in boy. Oh, at hotmail.com. Euclid UB. The last letter is B as in boy. Oh, yikes. Maybe you want to read it back to me just to make sure I said all that properly. That's correct. And then, okay, no, you go ahead. You go first. Okay, great. And do you need the address of the new home? It's basically on the corner of 7th Street and Cactus. Okay, when you email me, I'll email it back to you. And then, what was my other question? Oh, the ductwork. When Giovanni came out to install the drop-down plan, I believe that was 2016. In your voice text, I don't know if that was just a typo, it said 2014. I believe the work was done in the summer of 2016. Oh, I did. I'm so wrong. I'm so sorry. Okay. Okay, thank you so much, Ruben. I appreciate it. Bye-bye.
Yes.
Sorry.
The sign is back to me.
Okay.
Yeah, it'll always be there.
There's no papers we got on.
All right, folks. It is 9:17. Let's get started again. I think everybody's back. So we're moving ahead to number 36. Everyone go ahead and turn the page and take a look at number 36. Now, as we proceed with word problems, we always want to continue thinking about the same four things. So we begin by drawing some sort of picture, then we figure out what equation we're supposed to solve, actually solve it, and then verify the truth that what we just came up with is actually true. So in this problem, let's go ahead and read it together. A ball is dropped from a cliff. Yep. So have you ever done that as a child? You were somewhere, a mountain, a cliff, and you throw something over the edge. Has everybody done that? Okay, no one raised their hand, but I'm guessing most of us have done that. Even though they tell you not to do it, why are you not supposed to throw things off cliffs? Because there could be someone hiking down there, and then you hit them in the head or something like that. They could go blind, who knows? So, a ball is dropped from a cliff. The distance s that it falls in t seconds is given by the formula s equals 16t squared. How many seconds will it take for the ball to hit the ground? So, what should we do first? Draw a picture. Let's draw a picture. So, I'm going to draw the ground, a cliff, me, the boyish grin, and a ball, which I then drop. Right? You notice I didn't throw the ball, I just dropped it. That's it, just dropped it. And then the cliff is 368 feet tall, so I'm going to write 368. And, well, is our picture done? Probably. I think that's about it. We dropped a ball off the cliff. It's 368 feet tall. Now, it says that there's a formula. They did actually give us a formula. The distance s that the ball falls in t seconds is given by 16t squared. And the actual question is, how many seconds will it take for the ball to hit the ground? So what's the question asking for? Yeah, time. How many seconds? So what are we trying to solve for, s or t? T. We're trying to solve for t. And in fact, just to remind ourselves of that fact, we can go ahead and say the answer should be t equals something. Now, if we're trying to solve for t, what do we put in for s? S is, again, the distance that it falls. And how far is this ball falling? 368. So we plug in the 368 equals 16t squared. And is that the equation? Yeah, I think so. So this problem is refreshingly more simple than the other problems that we've done, right? Our drawing was nice and basic. Someone dropped a ball off a cliff. They gave us a formula, kind of like we knew the Pythagorean theorem was a squared plus b squared equals c squared. We just plugged in the numbers. They gave us the formula s equals 16t squared. We just plug in the number. And now we're on to phase 3, solve for x. So go ahead, everybody, solve for x. Divide that 16 over. It's what?
23.
Oh, 23. So if you divide both sides by 16, apparently it's 23, so 23 equals t squared. Now technically, which of the 4 methods are we doing? Square root property, factoring, completing the square, quadratic. This is the square root property, right? Because we're about to square root both sides. That's all the square root property means. If you take the square root of both sides, you're doing the method 1, square root property. And so we square root both sides. Oh, and we get t equals the square root of 23. Now technically that's plus or minus the square root of 23. Because remember, anytime you square root both sides as an action step solving algebra, you have to do plus or minus. But could it take negative time? No. So that we know is an extraneous solution. So time is either negative root 23 or positive root 23. But we know that the negative root 23 is extraneous. And I suppose we just write extra. That's fine. So how long is root 23? 4.797. Thank you very much, Roy. So our solution is going to be t equals the square root of 23, but you wouldn't say that to someone. You would say 4.797. Now what did they say? Round to the nearest tenth. So what should we really say? 4.8 seconds. Now again, what's the exact answer to this problem? What's the exact answer? Root 23. Root 23 is the exact answer, right? That's exact. But would you ever say that to your friend? Like, hey, let's go to the mall. I'll be over in root 23 minutes. No, like your friend would think you're a jerk, right? That's not very nice. You don't say that to a friend. Instead, you'd say, I'll be over in 4.8 minutes. Now, even then, would you say 4.8 minutes? No, you'd probably say 5 minutes or something like that. But the answer to the problem is 4.8 seconds. Do word problems always have to be long? No, that one was nice. It was a nice basic problem. Why did that take so much less time than the other problems that we did? They told us the formula. The formula was simple. And the drawing was easy too. It wasn't a geometric figure like a rectangle or a square. It wasn't a rug in a room. It was just a simple idea of dropping something. Okay, how about number 37? It says the position of an object moving in a straight line. Well, what's an object that moves in a straight line? A car, a train, a plane, you when you're walking. So it just says the position of an object moving in a straight line. So let's just show that. Here's an object, and it's moving in a straight line. Now it says the position of the object moving in a straight line is given by, once again, s equals 2t squared minus 3t. Where s is in meters, so I'm going to go ahead and say that. This is distance in meters. And t is time in seconds. So t is seconds. And it says t is the time in seconds the object has been in motion. So a quick question, how far has the object gone after 0 seconds? After 0 seconds, how many meters has it gone? 0. Now that's intuitive, right? You're like, well, if it's times 0, it hasn't moved at all, so it should be 0. But in fact, if I plug in 0 into this equation, does it give us the answer we expect? What happens if I plug in 0?
0.
You get 0. Okay, well good. So that matches our expectation. That this formula means that this point right here is the genuine starting point. That the object has not already been moving. It started off right there at t equals 0. So at time 0, it was motionless. It was just sitting there, waiting to go. Okay, so the question is, how long will it take the object to move 9 meters? So they gave us a 9. We plug that into s or t? We plug it in for s, right? Because they're saying how long until it moves 9 meters, And I very carefully labeled my S to remind me that S is meters, T is time. So definitely we'll plug in the 9 for X. So now we have our equation. 9 equals 2t squared minus 3t. And we are now on to phase, well, let's see. We drew our picture. The picture wasn't very much. We understood the equation they gave us. We have our equation now, and now we just have to solve. So what's the first thing that we always want to do with a quadratic equation? Yeah, we want it to be in standard form. We need the whole thing to equal 0. Typically, that's your best bet, is to make the whole thing equal 0. So what should I do? Move the 2t squared and the 3t to the left, or move the 9 to the right?
9 to the right.
Yeah, I'll probably just move the 9 to the right. But then I'm going to write it as 2t squared minus 3t minus 9 equals 0. Am I allowed to do that? Just flip-flop where the equation sign is? Yeah. So it still equals 0.
Simple question. If you would have 2t and negative 3t to the other side, you're going to be able to calculate that?
Well, that's a good question. Had I moved, as you're suggesting, if you had moved the 2t squared and the 3t to the left, then it would have been a positive 2t squared over here, right? And then it would have been a positive 3t over here. And you'd have had 2t squared plus 3t plus 9 equals 0. What's the difference between... Oh, I did that wrong. That was a negative, so that should be a positive. That's a negative. There we go. So there. It could have been negative 2t squared plus 3t plus 9, but I have 2t squared minus 3t minus 9. What's the difference between those two equations? In this one, which one's negative? Just the 2t squared. In that one, what's negative? Everything else. So effectively, what's the difference between these two equations? All the signs are changed, right? This goes negative, positive, positive. That goes positive, negative, negative. Which is the right equation? They're both correct. They're both correct because what can I do to this equation to turn it into that equation? We can just multiply the whole thing through by negative 1, and then I would have 2t squared minus 3t minus 9. So, Uriel, thanks for asking that question. This points out that we're free to manipulate the equation, right? We can manipulate it to make it easier for us. So if you prefer to have the t squared term positive, you can, just by multiplying through the whole equation by negative. But if you prefer those two terms are positive, you can. You're allowed to flip-flop all the signs if you want to, because all you're really doing is multiplying the whole equation by negative. But let's go ahead and solve this one. The one that we had from get-go. So how would you like to solve it? Would you like to square root property? No, that's not available to us. Factor, we could factor. We could complete the square if you really wanted to, but since there's a 2 up front, that makes it a little less optimal. Or the quadratic formula. I think probably the quadratic formula is the least amount of work right now, because all you have to do is use your a equals 2, b equals negative 3, and c equals 9. Oh, negative 9. So probably that's the least amount of work, but if you wanted to factor it, you could. So I haven't reminded you to do this today, so I'm going to remind you right now. Whenever you do the quadratic formula, I would write it once. So just remind yourself, negative b plus or minus the square root of b squared minus 4ac all to 2a. And then after you write it once, what do I recommend you do? Yeah, you write it empty so that you leave a space for all those numbers to get plugged in. It's a very good best practice to make sure that you're going to type all those numbers in correctly with the parenthesis in the right location, because you're about to type all this in your calculator maybe, and you want to be very careful. So let's see. Negative b is negative 3, and then negative 3, 2. So it really helps to use all those parentheses, because now when you go to your calculator and start simplifying all that, you're just doing every little piece at a time. Like the negative 3, I'll do that part first. That's just a 3. And then inside the square root, negative 3 squared, that's just a 9. And then negative 4 times 2 times negative 9, that's plus, what? 4 times 2 times 9? Is it 72? I think. Over 4. Well, this problem really worked out. I always get so excited when the number inside the square root is actually square rootable. It's like something nice happened to you this day. Oh, nice. The problem is square rootable. So that's square root of 1 all over 4. The square root of 81 is just 9. So now we have our two alternate realities, 3 plus or minus 9 all over 4. And again, I use two little arrows to show my two alternate realities of my two answers. I could either have 3 plus 9 over 4, which is 12 over 4, which is 3. Or I could have 3 minus 9 over 4, which is negative 6 over 4, which is negative 1.5. So again, using our vocabulary, we have two answers. Okay, there are, in fact, two solutions. Both of those numbers, if you plug them into the original equation, it will make them true, which you should take the time to do. Actually go back and check. If I plug those numbers in, will it make it true? But only one of them is realistic, right? Which is the realistic answer? The 3. Because an object can only move with positive time, realistic, 3 seconds. Whereas we call the negative 1.5, what do we call that solution? Extraneous. That's extraneous. Yeah, absolutely. Any test or final exam that you take, whenever you get solutions to a problem, you would need to take those solutions and first do a quick check. Is one of them extraneous? Do they both make sense in the context of the word problem? No, negative 1.5 doesn't even make sense. But you would take the 3 and you would still plug it in and say, is 2t squared minus 3t minus 9 equals 0? If I plug in 3, it what? Oh, you definitely need to write extraneous. Yeah, that is a requirement. You'd have to write, this one's extraneous, this one's correct. And is this right? 3 squared is 9 times 2 is 18, minus 9, minus 9. Oh, good, yes. In fact, 0 equals 0. And that is the end of the problem, right there. When you get to a true statement, the true statement is the end of the problem. Not x equals 3. The true statement is the real end, because that's how you know that everything you just did is correct. That's step 4, verify the truth. Now that I'm done with all 4 steps, I would report my answer. And I would say, okay, the answer is, how long will it take the object to move 9 meters? T equals 3 seconds. And that would be my answer that you would report. But the end of the problem was verifying the truth. All right. Well, folks, those were six, right? 6 mighty fine word problems. Those were good word problems. Do you know what I would recommend that you do now? Well, obviously, you have to go home and practice because you'll have problems like that on my math lab. So when you go home tonight and you go on my math lab, you'll have problems just like those, and you can go back and look at your notes to remind yourself how to work through those problems. When would I do these problems if I were you? Today. I'll do them today while it's fresh in your mind, right? Do it today. Okay. Well, that's it for these particular word problems. Now we're moving on to section 1.6. Section 1.6 is fun because it is an application of quadratic equations. Again, those same 4 methods to solve a quadratic. But these equations don't look like quadratics. But in fact, they are quadratics in disguise. Does the very first one, root x plus 3 equals x minus 3, does that look like a quadratic formula? I mean, just looking at it, does it look like ax squared plus bx plus c? No, definitely not. Do you believe me when I tell you that it is a quadratic equation? You probably believe me just because you know I wouldn't be asking it if it weren't true. So how is that equation a quadratic in disguise? That's what section 1.6 is about, quadratics in disguise. So what do we have to do to that equation? Yeah, folks, what Miranda just said is a great point. What would you always want to do with a square root? Get rid of it, right? You'd always want to get rid of a square root. It's just like fractions. You want to get rid of fractions if you can. You want to get rid of square roots if you can, because those things are complicated. You want to get rid of them. So how do you get rid of a square root? If I have root x plus 3 equals x minus 3, how do you cancel a square root? Square it. So we are going to square both sides. Now notice that's the opposite of the square root property. The square root property, our first method for solving quadratics, is when you square root both sides. What we just did was square both sides. Same essential idea. you're just doing algebra. It cancels out the root, and now you have x plus 3 equals x minus 3 squared. Now does it look like a quadratic? We're getting closer. What do we ultimately want to do? We want to put it in standard form. And folks, what is standard form? Standard form is equals 0. You want the whole thing to equal 0. So you have to FOIL anything, like the x minus 3 squared. You have to move all your terms to the left. So that's standard form. Multiply anything, and then move all the terms to the left. So again, you might want to show a little bit of scratch work to do the x minus 3 squared. You can do that somewhere else on your paper if you want to. You just go somewhere and say, okay, x minus 3 squared. Because you might be able to do that in your head, folks. I'm not sure where you are. But you would at least want to write out the x minus 3 times x minus 3, and then you do FOIL. And that would be x squared minus 3x plus 3x plus 9, which is x squared minus 6x plus 9. So there's my work for doing the actual FOIL process. And then you can go back to where you're actually doing your equation and write down x squared minus 6x plus 9. Again, as much as possible, you want to keep your equation clean. You want to make it look clean. As in, don't necessarily do scratch work right there where the equation is. If you could do it somewhere else and then come back and keep the process going. Now what do I do? What do I do? Brent or Brett? Yeah, get everything over to one side. Now, should I move the x squared, the 6x, and the 9 to the left? Or should I move the x plus 3 to the right? Probably the x plus 3 to the right. Right? Now, is it the same? It's the same. Either way, it's up to you. Typically, I say move everything to the left. But in this case, since I have 3 terms on the right and only 2 on the left, I'll just move things to the right to make it a little easier. So I subtract my 1x from both sides. That cancels it. And I subtract my 3 from both sides. That cancels it. And now I have 0 equals this, which is x squared minus 7x plus 6. So that part you can choose, right? You can either move everything to the left, or you can move it to the right and then just move your equals 0. Okay, so now everyone agrees that this is a quadratic. That really was a quadratic equation in disguise. So what method do you want to use? You could complete the square if you want to, although that could be a little challenging because with completing the square, you have to move that term, the n term to the right, and then you have to take half of 7. And that might be a bit of a bummer to do half of 7 and then square it to get 49/4. And then you're adding 49/4 to both sides.
I mean that one. I meant the 2 numbers at.
Yeah, yeah. Oh, I agree. Not completing the square, that'd be a little complicating, but factoring. Factoring would be great. What 2 numbers multiply to make 6 to add to make 7? Yeah, 6 and 1, right? 6 times 1 is 6. 6 plus 1 is 7. But they both have to be negative. So it's really x minus 6, x minus 1 equals 0. Yeah, in this case, factoring was faster and easier than doing the quadratic formula. And then you set both of those factors equal to 0. And what do we end up with? Yeah, either x minus 6 equals 0 or x minus 1 equals 0, which means x equals 6 or x equals 1. Now here's a tough question, a tricky question. Are both of those realistic answers? Like this isn't a word problem. It's not about the length of a rectangle that can't be negative. It's not about the time it takes something to fall, which can't be negative. And plus neither of those are negative. So are both of those the correct answer? It seems like it. But unfortunately, you know, I'm giving you a definition right now. Remember when I told you that when you're doing algebra, like say x squared equals 4, and whenever you square root both sides in the action of algebra, what do you have to do when you square root? It's plus or minus, right? The square root is only plus or minus if it's an action step during algebra. That square root is part of the formula. That square root is there. It's part of the formula. It only takes the plus solution, and that's it. So go ahead and put a little plus in front of it. Anytime you see a square root in an equation, it is assumed that you're strictly speaking about the positive square root. And that's it, just the positive square root. It's not plus or minus. That's only if you're doing algebra and you square root both sides, then you get the plus or minus. In a formula, it's just a plus. So, all that said, let's check our solutions. Is 6 the correct answer? Let's check. That would be the square root of x plus 3 equals x minus 3. And that would be the square root of 6 plus 3 equals 6 minus 3. And that would be the square root of 9 equals 3. And what is the square root of 9? 3, but only the positive 3. Did that work? Yeah, that's true. So definitely so far, x equals 6 is a correct and valid solution. Now let's try x equals 1. Is x equals 1 a solution? If I do x plus 3 equals x minus 3, and I plug in 1, so that's 1 plus 3, and then that's 1 minus 3. That's the square root of 4 equals negative 2. But the square root of 4 is strictly positive 2. And is positive 2 equal to negative 2? No. So that is false. And therefore, even though this was not a word problem, it is still possible to have an extraneous solution if you're dealing with a problem with square roots, if the problem itself has a square root. Because if the problem itself has a square root, it's assumed only positive. So here's the subtlety. How many solutions did the original problem have? 1, right? The original problem just had 1 solution, and that is x equals 6. The only answer is x equals 6. But we didn't solve the original problem, did we? What did we do to the original problem? We squared both sides, and then and the act of squaring both sides, we actually changed the equation, didn't we? All right? I really want to point this out to everybody. This problem has 1 solution, but we squared both sides and we turned it into a quadratic. And a quadratic has how many solutions? 2. So this equation had 2 solutions, but this was not the original equation. The original equation only has 1 solution. It just so happens that in order to solve it, we squared both sides, creating a different equation that had 2 solutions. So one of these 2 solutions was extraneous because the original problem only had 1 solution. I'd like to show that to you folks, because this builds on our understanding about what a solution even is. What is a solution? What is it you're finding when you solve an equation for x? Anytime you solve a quadratic and you get x, what is x actually? On the graph, it's an x-intercept, right? Everybody take a look at this original equation. Square root of what, x plus 3? Equals x minus, well, first of all, just look at the x plus 3. How many times does that thing touch the x-axis? Once, right? And now we're asking, when does that equal x minus 3? Now this is the full equation. How many times does that thing touch the x-axis? Just once. Where? 6. Now we took that equation and we squared both sides. Now that gave us x plus 3 is equal to x minus 3 squared. Now look at that picture. Oh, hold on a second. Oh, it's tough to see. Okay, there we go. How many solutions does that one have? 2, right? It goes through the 6 and it goes through the 1. So in fact, the blue equation, the one that was squared, has 2 solutions. The red equation, the original one, only has 1 solution. So since we wanted to solve the original problem, the answer of 6 is correct. It just so happens that by squaring that equation, we created another equation that did in fact have a solution at 6, but it also had another solution which was extraneous. So clearly, we have to be very careful about considering what our answer x equals 3 equals. And folks, that's why x equals 3 is never the end of the problem, right? I think that's more of like a high school feeling, like, hey, I solved for x, I'm done, move on. X equals is never the end of the problem. You actually have to plug those values in to the equation, see if it makes it true or not. And once you get to the true or false statement, that's when you know that it's the end of a problem. Okay, great. Moving on. How about number 39? Does that look like a quadratic? It kind of looks like a quadratic, right? What about it looks like a quadratic? Yeah, it looks like standard form, first of all. You've got something to the 4th power, and then minus something to the 2nd power, and then plus a constant equals 0. So it really looks like a quadratic, but it's not a quadratic. Why? Yeah, it's supposed to be to the power of 2 and to the power of 1. But this is to the power of 4 and to the power of 2. So it looks a little different. All right. Well, folks, here's what we're going to do. I'm going to teach you a method called substitution. It's actually called, well, you can call it anything. It's typically called U substitution in calculus. So first things first, everyone rewrite the same exact equation, but I want you to notice something. X minus 1 to the 4th is actually the same as x minus 1 squared squared. Do you agree? That x minus 1 to the 4th is actually the same as x minus 1 squared squared. How do exponent rules work? If I have, I'm going to use my letter u here. If I have u to the power of 3, and then I raise it to the power of 4, what do exponent rules say about what that's equal to? U to the power of? Well, let's convince ourselves, shall we? First of all, what's u cubed? U times u times u? Does everyone agree that u cubed is u times u times u? And how many times do I have to multiply u times u times u times itself? 4 times. So now I have u times 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 u. 1, 2, 3. 1, 2, 3. 1, 2, 3. And how many u's do I have multiplied together? 12. Okay, so we're all convinced that this answer is u to the 12th? Okay, so what's the rule then? When you raise an exponent to an exponent, what do you do with the exponents? You multiply. That's the rule, right? Okay, so everyone back to here. Do you all agree that x minus 1 to the 4th is the same as x minus 1 squared squared? Yeah, that works. Okay, let's finish rewriting the problem. We have x minus 1 squared squared minus 5 x minus 1 squared plus 4. Now this might be a technique that you haven't seen before. It'll look similar because you've all done substitution before. But this is definitely a technique you do in calculus all the time. And again, it's called U substitution. And that's why I'm using a little U over there. That's, what is that, a Greek letter? It's a Greek letter U. It's technically mu. But let's all use the Greek letter U. Here's what we're going to do. We're going to let U equal x minus 1 squared. And everywhere you see an x minus 1 squared, we're just going to write U. And this is an act of substitution. So what is my new equation? U squared minus 5u plus 4. So by doing that act of substitution, we really cleaned up our equation quite a bit. We simplified our equation, and now does that look like a quadratic? Well, yeah, that's just a real basic quadratic. How can we solve it? What would be fastest? Square root, factoring, complete square, quadratic. Factoring. Factoring should be our go-to, because if you can factor, factoring is quick. And sure enough, what times itself equals, well, no. How do you multiply to get 4 that you had to get 5? Yeah, 4 times 1. 4 times 1 equals 4. 4 plus 1 is 5, but they both have to be negative. So now we have mu minus 4 and mu minus 1 equals 0. And now we can do the zero product rule, set them both equal to 0. So mu minus 4 equals 0, or mu minus 1 equals 0. And therefore, it could be that mu equals 4, or it could also be that mu equals 1. Did we finish this problem? No, because right now we solve for mu. We solve for mu. We don't want to solve for x. I'm sorry, we don't want to solve for mu, we want to solve for x. So how do we finish this problem?
X minus 1.
Yeah, well, you're really close there, Allison. In fact, you might have said what you meant, and I just didn't hear it. You're going to set x minus 1 squared equal to 4, and then you're going to set x minus 1 squared equals to 1 and solve those. So, okay, yeah, I thought that's what you meant. So now let's go ahead. We know that mu could be 4, so we're going to say one possibility is that 4 equals x minus 1 squared, and the other possibility is that 1 equals x minus 1 squared. Those are two possibilities, right? So we did substitution to make our quadratic simple, and now we're substituting back in for mu in those original problems. By the way, folks, how many solutions should we have? 4, right? The highest power on x tells you how many solutions you should have. So 2 solutions was too few. We need 4 solutions, and that's what we're going to get by doing this. So how do we solve these? Yeah, the square root property. We just have to square root both sides. We square root that and that. And since we just square rooted during algebra, what do I put in front of the 2? Plus or minus. So one possibility is that x minus 1 is equal to plus or minus 2. I go ahead and add my 1 over there. And that tells us that x is equal to 1 plus or minus 2. And again, I'll show little arrows to show my 2 possibilities. Either 1 plus 2 is equal to 3, or 1 minus 2 is equal to negative 1. So that's 2 of my solutions, 3 and negative 1. And then we'll go back over to the x minus 1 squared equals 1 and solve that one as well. And that will give us 2 more solutions. So I square root both sides here. That's plus or minus 1 equals x minus 1. Add the 1 to the other side. And now we have 1 plus or minus 1 equals x. And again, that's 2 possibilities. Either 1 plus 1 equals 2, or 1 minus 1 equals 0. Wasn't that exciting? What an exciting problem. That we knew from get-go that we'd have 4 solutions. So we changed the equation by using u substitution into a simpler quadratic to solve for the first 2 solutions. And then plugging those into our u substitution, we got further our other solutions. So what are the solutions in order from smallest to greatest? And negative 1, and then 0, and then 2, and then 3. Are those correct? Because remember, that's not the end of the problem. All we just did was write down x equals. X equals is not the end of the problem. How do we know if we're at the end of the problem? We should get true statements, right? We should get true statements. That's the end of the problem. So you would go through and plug each of those 4 answers into the equation and see if they're true. Now, are we going to have any extraneous answers this time? It's not a word problem, so there's no extraneous solutions because it doesn't make sense in the context of the word problem with negative length or negative time. Is there any square roots in here? No, there's no square roots in the problem. So in fact, they will all be solutions. There's no extraneous solutions here. So I'm telling you there's no extraneous solutions because it wasn't a square root and it wasn't a word problem. But are those solutions actually correct? Did anyone already check?
I checked for 3 and 2 there.
Okay, great. How else can you check besides plugging them in? Did anyone check the last page?
Yeah.
No. They're correct. Okay, we got them right. So great. Now you'd still want to go through and plug everything in and check, right? But otherwise, that's the end of the problem. So what I will tell you, folks, is I'll put one of those on your test, right? At least one problem where it's not a quadratic at face value, but you have to change it into a quadratic, and then double check for the extraneous solutions. All right. That was section 1.6. And that was literally it. That's section 1.6. There were just 2 problems to look at. You'll probably have 1 more of each of those on my math lab to practice. But otherwise, that's it from section 1.6. It was just looking at equations that aren't quadratic, but they are quadratic in disguise. All right. Folks, I have a gift for you. I didn't pass it out at the start of class because I didn't know if we would get to it. How do you feel about the way I use the word gift? Because what is a gift from me to you? Work, right? Some sort of a sheet of paper with information on it, and then you're going to do it. So maybe the word gift, you're like, oh, Mr. G, that's really not a gift. It's not like a Christmas gift or a birthday gift. But it's a gift of knowledge, right? Are there 2 previews? Go. All right. So folks, this little gift I just gave you, what I'd like to do is work in a group. There can be 2 or 3. Like for instance, there's 3 of you in this row. You can all work together. But if there's 4 of you in a row, there could be just 2 and 2. What I'd like you to do is just by looking at this, tell me the rules for how to make a number line and tell me the rules for how to write it in interval notation. Okay, because I think you've all seen this at least once before. But even if you've never seen it before in your life, You should be able to look at this like Sherlock Holmes and figure out what's going on here with these three different notations. The one thing I'll go ahead and tell you is, in terms of labeling, right up at the top, all the way at the top, the first column represents, well, inequality form. So the first column is writing it in terms of inequality notation. So that's inequality notation. Oops, notation. The second one is just a number line. You know, what are the rules for a number line? And then the last one is called interval notation. So I would like you to be able to look at this, considering it like data, like you're an archaeologist, maybe, and you're looking at a society and you're trying to say, geez, why would they make all these markings the way they did? And come up with an explanation, and your explanation should specifically point out what the rules are for the inequality symbols. You know, what's the rule if it's less than or equal to versus just less than? What's the rule for open circle versus closed circle versus going off forever with an arrow? And what's the rule for bracket versus parenthesis versus infinity? Right, so these are the things you want to figure out. So again, you might remember all this off the top of your head from your previous math class, but at the very least, go ahead and consider this. I'm going to give you all 5 minutes. So for 5 minutes, work with a couple team members and come up with the rules for how these things work. Go ahead.
And I know that here meaning this one. So that means
All right, folks, I hear the volume in the room is a little quieter. So I'm guessing that means that you're pretty close to being done with your conversations. So let's jot down the rules for what these symbols mean. And what I'm going to do is I'm going to cluster the symbols together. So for instance, what we're looking at is inequality notation, and then the number line, and then the interval. All right, so when the inequality symbol is less than or greater than, what should that look like on the number line? And let's just see here. I'm really trying to call on everybody at least once. I think I probably have. Does everyone feel like I've called on you at least once? No, tell me your name again. Daniela. Daniela, that's right. Daniela, what will it look like on a number line if you use a less than or greater than symbol?
The would be hollow?
Yeah, it would be a hollow circle. We call that an open circle. You would use an open circle on the number line. Absolutely right. So if it's less than or greater than, use an open circle. Whereas on the interval notation, what would it look like? If you use less than or greater than, what would the interval notation look like here? Parentheses. Absolutely right. So those symbols go together. If it's strict inequality, we call this one strict inequality, meaning they can't be equal to each other. Then we use an open circle to represent that and parentheses to represent that. Now, that word strict inequality, meaning that you're either strictly less than it or you're strictly greater than it, another part of what that means is that it's not equal to. So by strict, I mean not equal to. And another way of saying not equal to is not included. So let's all do a nice little example with this. Let's say that I gave you the inequality, x is less than 5, but greater than 1. That's the amount of money I have in my wallet. It's less than 5, but more than 1. So if that's my inequality, what would my number line look like? I would have a 1 and a 5, and what kind of circles would I put on it? Open circles. And then where would I shade? Everywhere in between. So again, this phrase not included is very important. Am I including 1 in the possibility of how much money I have in my wallet? No. 1 is not a possible answer. I'm not including 1. I strictly have more than 1. I could have $1 and a penny, or $1.05, or $1.50. But I don't have $1 in my pocket. I have between $1 and $5. So I use the open circle to be not included. Am I including 5 in the possibility? No, I don't have $5 in my pocket exactly. I could have $4.99, I could have $4.98, but I'm not including 1 and 5. So this is an important way to interpret this. When you say x is less than 5 but more than 1, you're doing strict inequality. I should have left that there. Strict inequality. Meaning I am not including the 1 or the 5 in my possible answer. So if I said I have between $1 and $5 in my pocket, in this particular case, between means but not including. All right? So then how would I put this in interval notation? I would use parentheses and I'd say, I exactly take it from the picture. I say parenthesis 1, comma 5 parenthesis. And that means I'm looking at all the numbers between 1 and 5, but not equal to 1 and 5. Now this is a little unfair, right? Because at every party you've ever been to, you played the game I'm thinking of a number, right? So if someone says, I'm thinking of a number between 1 and 10, are you allowed to say 1? Is that a possibility? Yeah. Typically, when you play the game, I'm thinking of a number between 1 and 10, you're allowed to guess 1 and 10 because in common English, amongst friends, we mean between means including the endpoints. But this is different. When you use the strict inequality, you're not including the 1 and the 5. Okay, how does that compare to, okay, that's it for those notes. All those symbols go together. If you wanted to kind of group them together in your mind, I might make a little circle and put less than, greater than, open circle, parenthesis. All those together mean not included. Means whatever numbers you're talking about, you're not actually including the numbers at the endpoints. Maybe I should say that. Not including the endpoints. Okay, well, what about less than or equal to, greater than or equal to? So what would the number line look like? Megan, what would you expect the number line to look like? If it's less than or equal to or greater than or equal to? What kind of circle would you have? Yeah, it'd be filled in. And we call that a closed circle. A closed circle. So if it's less than or equal to or greater than or equal to, you use a closed circle. And the act of shading means you're including that number. In fact, that's what shading means. You're including the number. After all, when I shaded that, what did that mean? I was including all those numbers. Shading means including. So when you shade in the circle, it means that you are including that number. And then what would the interval notation look like? If you have a less than or equal to, greater than or equal to, or closed out, what would the interval notation look like, Robert? what would you use on your interval notation if you are including the number with a closed circle?
It look like this. Or that one. Okay. So it'll be a filled in circle.
It would be a filled-in circle, and then what kind of symbol would you use?
Let's see, or bracket.
Bracket, exactly right. So that would be bracket. So we use brackets and closed-in circles to mean included, meaning it could equal, right? So this is could equal. I could actually equal the number. And that means I am including it. And this is what we would all agree with. If I said, pick a number between 1 and 10, this would be the symbolic notion for that old game, pick a number between 1 and 10. And then what would the number line look like? You'd go from 1 to 10, and you'd use shaded in circles to mean you could actually be equal to 1 or 10. And you shaded everything in between. And then what would the interval notation look like? Julian? What would the interval notation look like for between 1 and 10?
2 brackets.
Yeah, it'd be bracket 1 and 10 bracket. Okay? Now, I realize this looks like a lot. Like you look at it, you're like, oh, I mean, so many different things. You've got inequality symbols, you've got the number line, you've got the interval notation. But it really just boils down to the word included. You either don't include the endpoints and use strict inequality, open circles, or parentheses, or you do include the endpoints and you use less than or equal to, greater than or equal to, a shaded in circle, or a bracket. And that means including the endpoints. This is like short notation. Like if you just want to memorize that, or I give you a test and you get the test and you immediately write down these two things to kind of remind you that these symbols mean not including the endpoints and these symbols mean including the endpoints. Okay, last question. How does infinity fit into all of this? What would infinity look like on the number line? Yeah, just be an arrow, right? It just continues off forever. That's infinity. What would infinity look like? Well, we don't really show infinity with an open circle or a closed circle, right? We show it with an arrow. Well, what does infinity look like on the interval notation? What symbol does what symbol does infinity take? Parenthesis or bracket? Always parentheses. Infinity always takes parentheses. And so I'm going to include my infinity right up here with not including two symbols. Infinity, whether it's positive infinity or negative infinity, always takes a parenthesis. That's just a rule. And believe it or not, that actually makes a lot of sense. It's not just an arbitrary notation. For instance, if I take a number line, so here's number line 1, 2, 3. Can I shade the number 1? Sure I can. I can put a closed circle at it. Can I shade the number 2? Sure. Can I shade the number 3? Sure. Can I shade the number infinity? Like, is infinity actually a number on the number line? It's not a number, it's an idea. Infinity is not an actual number. Infinity is a direction, right? Infinity isn't on the number line. Infinity is a direction. So can I shade infinity? No. And that's why it's not included. You can't actually get to infinity to shade it. And therefore, infinity is not included by virtue of the fact that it's not a number on the number line that you can shade. So it does make a lot of sense that infinity should always take a parenthesis because you can't shade it. You can't actually get there. Okay, folks, well, those are your interval notation rules. And that just gives you a nice little overview showing every possibility. What's the last rule we didn't talk about? The U. Exactly. What does the U mean? What does the symbol U mean? Yeah, U means union. And technically in English, what does the word U mean? You can tell by looking in the inequality notation. What does the letter U mean? They never cross. They go off in two separate directions. That's correct. But what word is used? Or. Union means or, right? And the best way to think of that is that you either go left or right, right? In every single number line, you go left or right. It means you have two different pieces that you've shaded with a gap in between. So union is when you want to combine two different answers that are shading in opposite directions. So that's what union means. It just means or. Okay, wonderful, folks. Those are the rules. So you can hold on to that sheet. I'm leaving it up there on the board. And perhaps what we all want to do now when we turn to our notes packet, so let's all go look at our notes packet. We're on section 1.7. The first thing I would do if I were you folks is go all the way up to the very top and make that shorthand notes. So on the one hand, I've got less than or equal to, greater than or equal to, a closed circle, or a bracket, and those all mean including the endpoints. Whereas strictly less than or greater than or open circle or parenthesis, that means not including. Oh, and I'm going to slip infinity in there too. There. I would probably just write that down on every page. Like as we go through these problems, just keep on writing those symbols down together as a group, and that way your brain will identify them with each other. Gee golly, I should ask, did I write them down correctly? Did I make a mistake? Did I group the correct symbols together? I think I did. Yeah. All right, well, folks, I'd like you to go ahead and try these. Right now is a challenge problem. I'll just walk around the room and answer any questions, but you guys go ahead and jot down the answers to 41 through 44 using those rules that we were just talking about. And notice the instructions are write the inequality in interval notation. So what I want to see is the interval notation with the parentheses and the brackets. But I'll give you a tip. The first thing I do for 42, 43, and 44 is I would draw a shaded number line. That is a best practice. Always draw the number line first, because that number line will make it obvious as to how to draw your interval notation. So go for it. Work with each other if you like. You can compare answers. By the way, folks, is the shading isn't very obvious in the first two, is it? Where are they shading? In between. Also, you'll notice this, well, yeah, like that just wrote on the road. There, that's helpful. You'll notice, what did they do that's different in this problem? They didn't use the circles at all, did they? They actually put the parenthesis in the bracket. They did that, well, I don't know why they did that. Normally it's supposed to be an open circle or a closed circle. But maybe they did that to make it more obvious about what symbol to use during interval notation. So what is the other problem? Since it's very good. Since infinity is on one side. Also negative. So that's negative. Oh, right, you're right. Right. Yeah, you got it. So, and then I would go flip it. So now we can see. Which way is it?
That's your number 5 then? That was what you showed. However, yeah, okay, yeah, just drop it. And how far would you show? All the way. Even past that, it'll show all the way to. There you go, it just keeps going.
Over.
Yeah, absolutely. It's between -7 and 4. And it is strictly less than. Yep, that's correct. And that's inequality notation. And now also provide inequality notation. So that's the inequality notation, and that's perfect. So now you want to write it down as an interval as well. Oh, very nice. Was this your example? Oh, wait, yeah. Why is it infinity? That definitely stops there. That's kind of the end point there. Yeah, it is a location because these prices and that circle. Oh, I see. That's not an arrow. That's a meaning it stops at 1. There you go. And so the two numbers are going to be -7. Yeah, that is an open circle. And you'll put these numbers in here in the same order from left to right. To the -7 and 4. There we go. That works? That's the X right there. That changes things? No, underline first. Yeah, wait. Wait, X is greater than Oh, do I underline?
Okay, I didn't finish walking around the whole room yet, but I only have 5 minutes left. So let's review these answers together as a group before you leave. So in the first one, number 40 is technically, that's an open circle and that's a closed circle. So if we were to write that in inequality notation, first of all, folks, the numbers always stay in the same order. So it's -7 on the left and 4 on the right. And then X would go in the middle, and we're saying X is less than or equal to 4, but greater than 7. And I use less than or equal to because it's a closed circle, and greater than because it's an open circle. So now, again, the numbers stay in the same order. So my interval notation would be -7, 4. But now I just choose parenthesis or bracket. So the first one is a parenthesis, and the second one is a bracket. Okay, so check your work, see if that's what you got. The second one goes from -5 to what? Infinity. I would go ahead and write infinity. Write it down concretely, folks. Put infinity at the end there. Because that way you know the two numbers that you're going to write down are -5 and infinity. And then, well, we're going strictly, well, for inequality notation, you would just say X is greater than or equal to -5. Because that's technically a closed circle, and you're shading off forever. So that's the inequality notation. X is greater than or equal to -5. But as far as the interval notation goes, it would be from -5 as a bracket to parenthesis infinity. Because you're going from -5 all the way to infinity. So that would be number 41.
Wait, why left? Going right.
It is shading to the right, absolutely. Yeah, it's shading to the right from wherever. So X is greater than -5.
Or equal to?
Yeah, greater than or equal to. I could have written that as X is greater than or equal to -5. Both of those are the same. And then, yeah, it's going from -5 to infinity. And you'll notice the two numbers here are in the same order as the numbers here. It looks just like a number line. Okay, so now we're doing X is greater than or equal to -5, and oh my gosh, that's actually the same problem. Isn't it? If you make a number line and you put -5 on it, it's greater than or equal to, so it's a closed circle. And it's greater than, so you shade to the right, to infinity. And so your two numbers are -5 and infinity. Same problem, -5 to infinity. And again, for these next two, walking around the room, some of you drew pictures and some of you didn't. I really recommend you draw the pictures. So how would I draw this as a number line? I would just go and put a -9 and a 3. I don't have to like tick, 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 tick all the way in between them. I'm just generally looking at it. And I know that -9 is a what? Open or closed circle? Closed. And then -3 is a what? Open or closed? Open. And X is everywhere in between, so I'll shade it. And then my number line, the number line literally is the interval notation. I take -9 and 3, I just write them down next to each other, and I use a bracket and a parenthesis. Hopefully, looking at those two things side by side, you see the interval notation. -3, thank you, oh my gosh, there. Interval notation really is just a number line. Interval notation is the number line, but without drawing it. Because mathematicians are lazy, they don't want to draw a number line every time. So they just draw interval notation, which is a representation of the number line. So how about this last one? My number line, I'm going from -5 and 7, and x is everywhere in between. But what is the 5, an open or a closed circle? -5 is a closed circle because it's less than or equal to. And then 7, is that open or closed? Open because it's strict inequality. And so that is my interval notation. It'll be -5 on the left, 7 on the right. Closed circle is bracket, and open circle is parenthesis. Okay, we ran out of time well, we didn't run out of time, class is just over. When you come back, folks, we'll do more inequalities. You don't have to work ahead in this. And in fact, please don't. You don't work ahead in the notes. What you do is you go home and you start working on the My Math Lab homework for all the problems that we've already done. So everybody tonight, go home, do the My Math Lab problems for what we've already done, and then I'll see you on Wednesday. Thank you very much. I have office hours right now if anyone wants to come up. Quite a few of you still need to come up to office hours before the day of your first test, which is next week. Next time. Yeah, I'll hand it out next class.
Can I come up with
Nancy.
some,
Yeah, you can come up right now. Yeah, of course. We'll just pack up.
Hey,
Hey there, Myra.
Hey, I have a question. I emailed you. So actually, basically, when is the credit